Okay, so one of the benefits of being late in the program is everyone's already copied or covered all of your material, and so you get to skip through most of your slides, which is great. The other thing that I sort of wanted to reflect on is really, I knew I was going to be late, and I thought, you know, it's late in the day, I don't want to go into the nuts and bolts, so I thought I'd cover more of some of the high-level trends and context for HPC. As we've sort of seen from the content of this conference, that HPC is many things to many people, and everyone has a different concept of what it is. There's always talks about strong scaling and parallelism in the core of HPC, but there's often many talks about other things that sort of surround HPC, and that changes over time. And one thing I like to do is look at HPC, but also to other areas that are happening, like maybe hyperscale or even enterprise IT, to look at those kind of trends and sort of see what's coming and what are the factors that could be affecting HPC in the future, and even things that may even disrupt HPC, or if not disrupt, but just change it in some ways. And so I just wanted to cover a couple of the things that sort of I see and I think that are real factors that are going to change HPC over time. We all know about HPC, so I don't want to say what HPC is, but I did want to show some of the commercial use cases of HPC, and this report really highlights some of the benefits of HPC to industry. So 2018, Hyperion did a study, and basically what they said is that for every dollar that industry invests in HPC, they get, on average, a return of $463 in revenue or cost savings. And actually, when at the bottom line, the net effect is $44, so at the bottom line. So what that means is put in $1 and get $44 of benefit out the other side. So the benefit's pretty clear cut. And the reason that you don't often hear industry talk about HPC is because high performance computing is typically core to their product or service development, and it is a competitive advantage, and people don't actually want to tell everyone else about their competitive advantage. So it's just one of those things that sort of goes unsaid. I've been in HPC for approaching 20 years, and I often wondered why we weren't getting all these enterprise and industry speakers and things at conferences, and it's often because people don't want to tell everyone else about what they're doing. Just go back for a sec. So one thing that we all know about HPC is it's traditionally been about simulation, being computationally intense. So we're calculating things based on mathematics or calculus. But that's actually changing, and obviously based on Melanie's talk, some of my data's out of date, but in science we're really encountering this data explosion, whether it's these mega science instruments and experiments, or just things like personal genomics. We've just got this massive amount of data, and we have it, on one hand we have this calculation intensive, like computational chemistry, for example, small inputs and small outputs, but huge amounts of calculation. And then on the other end we have huge amounts of data, and we need to crunch through that data, and whether it's streaming it in and flipping the bits and then streaming it out, or whether there's actually a lot of calculation and parallel calculation. One thing is certain, and that is that every time there's a resolution upgrade or a change to these instruments, the amount of data just goes up again. So the beauty in science is we typically do good things around files and file sizes and file formats like NetCDF and HDF5. There are certain cases in certain disciplines where they do insane things around numbers of files and sizes of files and I/O behavior, but we try to beat that out of them. One thing that we're not alone is that this data explosion is not just happening in science, it's actually happening everywhere. And I think the one thing that's really led to this recently is mobile phones. So everyone's walking around, they're sending texts and WhatsApp or whatever, and sending photos and videos, and okay, data's exploding. And you've got these businesses that are literally built on data. Data is, as they say, data's the new IP, data's the new gold, data's the new oil, all these things. It really is. And they're building new companies and new platforms entirely based on data. But Mobile is just the first step. Mobile is, yeah, we're awake and we start sending messages, but when you start to talk about connected devices, and when we start to have 200 million devices online and they're sending data 24/7, it becomes a much greater problem, and just processing that data. And so basically when we start to see these things converge, we're going to have what they call the data tsunami. And so in 2020, they predict that the world will create 40 zettabytes of data. That's a huge amount, orders of magnitude ahead of where we are. And they're saying, well, it's going to have 37% of significant business value. I don't know who comes up with these numbers and where they get them, but okay, it means that it's going to be of value. I need to process that amount of data and derive the value, and that's really the key. The other thing to remember is that when we move to a world of connected devices, there's no longer a human in the loop. And I think one of the trends around HPC is that we're still in the dark age of people, connect from a terminal and use the command line and type a script and submit a batch job and expect output. The world of the future is not like that. The world of the future is machine to machine, and it's basically built on APIs and metadata and software communicating with software and taking action. One thing around AI, we're basically encountering AI every day. I mean, this is not the thing of androids and personal assistant robots and things like that. It's really narrow focus AI, but it is data-driven artificial intelligence. And whether that's machine learning or whether it's any system that really passes the Turing test, whether it's hand-coded or deep neural networks, it's really assistants and tools that are basically sifting through this data and taking action. And it's not just these tech companies that are built on data and exploiting that data. It's actually really moving into the enterprise. And so one thing that working for HPE gives me is sort of that enterprise view. Even though I work in HPC, I get to see what the trends are in enterprise. And basically, the top priorities of all CEOs is I want to do AI and I want to do advanced analytics, because they've realized that data is this thing that we can mine and take action. And it's not just big data and Hadoop and those things. I mean, they came around 10 years ago. The world has shifted. The expectations have shifted. It's not good enough to just tip in all the data and put it into the data lake and do some analytics in the data warehouse and say, hey, the new product should do this. It's actually, we need to take action now. And when your customer's standing in front of you, you want to have that data and you want to have the recommendation right now. And so the expectation has moved to become real time. And so people want to implement real-time analytics, and that means even more computation. These are some of the examples. I just like the pictures, so that's why I showed this slide, but it really highlights the fact of real time. So if you're in Formula One racing, you instrument your car, it's a mobile platform, and it's sending all this data to the pits. The idea is that you can process that data and come up with some insight and change your race strategy to win, right? There's no point analyzing it 2 weeks later because you can't change your strategy. It's all about, we need to make changes now and do things. Should we bring the car in? Should we change the tires? Should we refuel now? The Seagate example is pretty similar to the one from the Jabil. Essentially, I've got this production line for electronic components. I want to basically detect any defects in the production line before they get sent out, and I have to recall them and things like that. But it's also, I want to understand what's going on in my production process and really prevent any downtime, so maximize my production. So again, I want to have a very short loop where I can detect a problem and take action. This is really an example of what that Seagate deployment is. It's a series of cameras. It's a series of computers. We have a line called Edge Line, which is essentially ruggedized servers that operate in elevated temperatures and vibration and think about factory floors or things like that. And processing that imagery in real time as the production items are moving down the line so that you can detect errors. So yes, there's a phase where we take the data and we do our training and we deploy our neural network, we develop our neural network, but then we deploy it into the field so that we can run this in real time. Now, when it comes to data, supercomputing and HPC has really been orders of magnitude ahead of enterprise computing in the rest of the IT world. So when we talk about big, our definition of big often has more zeros on the end. Obviously, Melanie's definition of big is more zeros than everyone else has. And I've reset my expectations today. But we've been dealing with big data for a long time. And we have techniques and approaches that are proven at that scale. And that scale is what the rest of the enterprise is about to encounter. So we actually have techniques and skills and understanding that benefits everyone else. I spend a lot of my time talking to customers about computer systems, and I really spend very little time talking about compute nodes themselves, but I spend more time talking about interconnects and actually storage, because the computer systems, you know, you add more money and electricity and floor space and you can have a very big system, but you need to be able to feed that thing. You need to be able to stream the data to it, and with an increasingly data-intensive world, the storage it becomes all important. We have a product, very long-standing product, been around since 1991. It's called DMF. It's just undergone a very significant design change, and it has a lot of new capabilities, so much so that we can manage many new types of file systems like Lustre, GPFS, XFS. We have all flash tiers, and very soon Weka.io as well. But the one thing DMF does is it allows you to stage data into an active form and have your very powerful systems operate on that data and then put it away and protect it. And we can store it on really economical tiers. We have different technologies such as our spin-down disk, and we can use even object stores in remote sites. But this is really about workflow integration and how do you keep those really fast computers running while dealing with the immense amounts of data. One of the really key parts of DMF is we actually redesigned the metadata part. So yes, you can have huge capacity, and that comes down to tape drives or disk drives or cloud capacity, but metadata is really about the numbers of files and the extended attributes. And we're talking about how do we deal with trillions of files or trillions of assets. And so what we did was actually take the prevailing big data technologies, so the SMAC stack, which is essentially Spark, Mesos, Apache Kafka, technologies such as that, so that are proven at scale and proven that with dealing with all these things, but giving us a fault-tolerant approach. Just on compute for a second, one thing that, you know, I think the rest of the world doesn't really grasp is that computing is only, you know, performant when it's in memory. You know, you really have to have data in memory, and yes, we can always employ more nodes and we can scale out to address more memory, but that imposes a barrier. You've got to adopt a scale-out approach very quickly on in your methodology. We built a really large shared memory machine, up to 48 terabytes of shared memory. So I can run simple program, I can run MATLAB, I can prototype, I can try things out. I've got a variable memory to core ratio. Think of this as more of a discovery machine for science, more sort of upstream process. And then once I've worked out my process, I actually want to then deploy it wherever cycles are cheapest. So whether that's on my parallel machine, if I need, you know, high performance interconnect, or if I've got an embarrassingly parallel machine and I've actually managed to, you know, decompose my problem and minimize that communication, maybe I can, you know, send it to the cloud or other things. But really, these kinds of systems are differentiating technologies that we have in HPC, and we know we have, but The rest of the world doesn't quite understand that these things are possible. This is a good corporate slide that probably no one in this audience knows what it means. Does anyone know what hybrid IT is? Hybrid IT is this concept that you don't just have on-premise machines or you don't just move to the cloud. You're actually going to use a mix of different resources depending on what's best for what you want to run. And so, you know, I might have public cloud or private cloud or government cloud or multi-cloud, meaning I can move between different clouds. And really it's this vision of, yes, I can just seamlessly migrate my workloads from one place to another. Everyone's familiar with this. We've had people talk about, you know, the issues of moving from a supercomputer center to a cloud type thing. And really the vision of hybrid IT is to just make that seamless. In my world, actually I think containers are the answer to this vision. I think containers enable the hybrid IT vision. And we heard earlier about singularity. I think singularity is really good because for people in a HPC, used to a HPC center, it's HPC people looked at containers and solved a bunch of the problems. How do you make it work in a secure context? How do you make it work with a high-speed interconnect? How do you make it work with a batch scheduler? How do you make it work with MPI? How do you make it work with parallel file systems? So it brings us the performance that we're used to and the operation in a HPC center, but it gives us that portability that we need with containers. And in fact, you know, this is an example for AI, but it really shows you some of the layers and some of the pieces that we use. And whether you want to do bare metal or containers, you know, there's different choices to be made in the different stacks. But the top level things are the same. It's just how do you choose to deploy? And if you really want that portability and the ability to run in different environments, I'd urge you to look at containers. And specifically Singularity, because it does actually address a lot of the things that we really value in HPC. HP is one of those big companies that buys other companies. You may have heard of one of our recent acquisitions, and that's Blue Data, or not. Blue Data is really a company that was born out of big data analytics. And in big data analytics, where think of Hadoop, there was this proliferation of Hadoop systems. So people would spin up a system to solve one problem, and then another one, and another one, and another one, and they ended up with silos of Hadoops. The issue was that, you know, every project needed a different system. And so what Blue Data did was say, no, we'll actually build an environment where we can virtualize that. So they use containers, and they build these adapters for storage. So early on the adapters were HDFS and NFS, and you could basically allocate resources to groups and give them this number of CPUs and GPUs, and you could connect them up to their data. And so you ended up with this virtualization of Hadoop. Now obviously, when you've got this big pile of data and you want to analyze it, if you want to do it with stochastic methods, you might use big data. But if you want to use new AI algorithms, you can kind of do the same thing. So Blue Data has been adapted for AI. But there's really no reason that you couldn't use this kind of approach for HPC as well. And to me, the best part about Blue Data is it's almost like the user-facing self-service dashboard of OpenStack, but it's for containers. And so it means that we can prepare containers and make them available in the catalog, and then users from these different project groups can basically select the containers they want to spin up and off they go. So it gives you that ease of use and usability. I think one of the biggest problems plaguing HPC is really that shifting expectation and generational change. If you look around the room, there's heaps of familiar faces. We sort of all turn up every year, and you know, it's great to see your friends, but there's this lack of young people keep turning up as well. My background's in software, and I like to keep abreast of software and what's going on. And there are many languages out there that are radically different to C and Fortran and things like that, and offer many advantages in developer productivity that I don't think we're really taking advantage of as a community. And I think things like these containers are really enablers. So these new researchers come along and they're used to these new languages or new paradigms, or they've come from the cloud, and they want to be able to be welcomed and be able to operate. They don't want to be forced into old ways or go away. So we really need to be more welcoming. Again, I mentioned that sort of data is really the center of the universe, and storing that data and then really acting on that data. This one's really showing really the edge, intelligent edge. I'll talk a little bit more about that in a second, but think of that as things deployed in the field with sensors, and then maybe a computer system or embedded processing nearby which can take action on that. And then maybe we do have some post-analysis and analytics, and then the core bits that we're interested in color, which are the large data archives or the parallel file systems or the training systems for AI. But one thing that I've really noticed is there's this new trend. It's known as fast data. And if you follow big data or Hadoop, you may know that Hadoop's kind of seen as dying in a way. And the reason for that is, like I was saying, it's really this post-analysis. And what's taking over from Hadoop is really systems like Spark, which is in memory, because I can get the answers quicker. But not only that, people are moving to more message-driven architectures. So I want a message bus like Kafka, and I want to publish my events. But with something like that, where I've decoupled all my modules or microservices, I can actually persist all those events, so that if something fails, it can just spring back up to life and replay that stream of events. And so from a software point of view, there's many, many new approaches that are really relevant. And not everything is parallelism to solve that strong scaling problem. Most of our problems, and actually I'd contend a lot of the throughput that we face, is really a problem with concurrency. So we build these parallel machines with high performance interconnects, and then we run throughput workloads on them where they don't use the interconnect. So if we think a little more about the actual workload that we want to run, and rethink those algorithms and architectures. I think, to Melanie's point, people are stuck in the past. They're stuck in this mode of thinking, and they don't look up, they don't look outside enough to see what's actually going on in the rest of the world. And maybe there's other ideas and approaches. One thing that really struck me, there's a link here to a video. It's called, I forget what it's called, The End of Cloud Computing. It's really, in other words, it's actually known as Return to the Edge. And what it talks about is this notion of cloud. Everyone thinks that maybe cloud disrupts HPC. I don't think cloud disrupts HPC. It's big computers in one data center versus big computers in another data center. It's Lustre, batch queues, all this stuff, versus Lustre, batch queues, all this stuff. That's not that different. It's just a different financial model or different deployment model, but it's not 10x. Like, there's not this radical shift. Whereas if you think about a car, like my son loves Teslas. He always talks about Teslas. I put this in for him, but if you think about a mobile platform like a car, it has all these sensors. Now, as it's driving down the road, it doesn't stream all the data up to the cloud and do the analysis in the cloud and then send the signal back, apply the brakes, that's a stop sign. No, it actually has to do all the processing on the car and decide in real time, because latency is the driver. Latency is the thing that is really going to change the world here, because we need to be able to take action in real time. There's a thing called the OODA loop, which is, for fighter pilots, it's everything. It's how short is your OODA loop. OODA is observe, orient yourself, decide, and act. Right? And the shorter you can go from observation to action, the more effective you are. Whether you're a fighter pilot, you're a Top Gun, or you've got devices like these, or you're in business, right? The customer's at the checkout. You recognize that's the customer. You present them with an offer of a discount or some other loyalty bonus. If the customer's walked out and you decide 10 minutes later, hey, that was that guy, it's too late. So latency, it's not just speed of light through copper or glass. Actually, latency in business is really the thing that's going to change, that is changing the face of IT. One real benefit of working for a very large company is that you get access to a huge product portfolio. And we're used to parallel supercomputers and what happens in the data center, but I personally think that what's going to happen at the edge and in those deployed platforms is really going to change things. Are we going to run simulations at the edge? I don't know. Are we going to run AI inference at the edge? Definitely we are. That's the difference between winning and losing the race, or really deriving value from the data that you have in a timely manner. That's it.